Hello everybody, Mr. Mark with you, and in this video I'm going to work with you on Snell's law and refraction. And so what I've got in front of me are the tools I need to do refraction, one being a protractor, so I can measure angles, and two being my scientific calculator. Now before we get started, it may have been a while since we've done things with angles, let's double check and make sure that our calculator is in degree mode. So I'm going to do the sine of 30 degrees, and make sure that I get 1/2. And so my calculator is in degree mode. So in this particular case, we're going to actually make measurements of angles for light, in this case red laser light, that is incident on this piece of glass in the picture. It is important to remember that when we measure angles in optics, we always measure from a normal, because this line right here may not actually be a line. It may be a curved surface, and we want rules that will always work. So I'm going to take my protractor and I'm going to line it up with the point where the light is incident. I'm going to go out to 90 degrees, which is up there, and then I'm going to construct and then label a line that is normal to that surface. So that dashed line is normal. And remember, normal means perpendicular to a surface. So this is a two-dimensional surface right here. Okay, so now when I take my protractor and I line it up with normal, kind of like that, I can measure the angle of incidence of the light on the glass. And so I'm going to use this to kind of extend that ray. You could obviously just draw it. And looking out here, looking at the inside, since this is a angle less than 90, so 60, 1, 2, 3, we'll say 63.5 degrees. We'll round that to 63 since we're just practicing here. Okay, so make angle measurements. Use them to calculate the index of refraction of the red light in the glass. So the incident angle, theta I, is 63 degrees. And we measured that from normal. So we had to measure where normal was. We had to measure the 63 degrees. So now let's apply our groovy new Snell's law. N1 sine theta 1 equals N2 sine theta 2. So if we're going to get the index of refraction for the glass, we can call that N2. Then the other angle we need to measure is the refraction angle in the glass. We also need to measure this angle right here. So theta R equals, so let's line our protractor up again. Actually, I need to spin it this way to measure the refraction angle. So line our protractor up. Again, I'm going to use my little triangle tool, extend that outwards. And that looks to be right at, we'll go ahead and call that 20 degrees. So our refraction angle is 20 degrees. Okay, so N1, since we're talking about air, will be 1. So I know everything I need to use Snell's law to solve for N2. So let's just go ahead and write it out like this. N2 equals N1 sine theta 1 over sine theta 2. And then let's go ahead and do our substitution. Even though N1 is 1, I'm still going to write my substitution. Like I didn't just forget about it. Sine 63 degrees. And then over our refraction angle, sine of our refraction angle, sine 20 degrees. And so we then get N2 equals Go ahead and grab my calculator. So I'm going to do sine. In some calculators, when you do sine or any other trig function, it will open a parentheses up. And it's kind of important here to pay attention to that. So I'm going to put the 63 in parentheses and then close it, just to make sure that the calculator doesn't try to take the sine of 63 divided by sine 20. Like, I want sine 63 degrees and then divided by the sine of, again, I'm going to do parentheses, 20 degrees. And when you do that, you get something crazy like 2.6. So relatively large index of refraction. Because this is a very, very different angle incident compared to refraction. Okay, so step B, calculate the speed of light in the glass. So we know that the definition of the index of refraction is the speed of light in a vacuum compared to the speed of light in that particular medium. So I can kind of rearrange this a few different ways. I can write the speed of light like that. And then I could write V equals C divided by N. And so since I have N for the glass, we'll say V equals C over N2 specifically. We'll call it V2. So the speed of light in a vacuum is 3 times 10 to the 8th meters per second. And then the index of refraction is 2.6. So notice that no matter where you use N, it has to have no units. Sine theta would be a ratio. This should be a ratio. And over here we have a ratio, meters per second over meters per second. So N doesn't have a unit. It's a ratio. So when we grab our trusty calculator and we do 3 times 10 to the 8th divided by 2.6. Nope. Here we go. I get something like, we'll call it 1.2 and then times 10. Remember, you can use like the little engineering function if you have trouble kind of doing the scientific notation on these sorts of things. Or you kind of go, well, 10 to the 8th minus a small number should still be 10 to the 8th. But I hit the engineering button, and that gives me 10 to the 6th, 7th, and then 8th like that to get it into a reasonable scientific notation number. So now, in just a few minutes with a few simple tools, we figured out the speed of light in this glass, 1.2 times 10 to the 8th meters per second. Okay, in part C, the same red light, so everything from up there still applies, is now incident on a glass air boundary. And so it kind of flip the situation around. Here we have glass, and then it's going to refract into the air. We're going to draw the ray. So this has an incident angle of 30 degrees. So I'm going to label that on here. This one's not drawn to scale, by the way. 30 degrees, and then let's draw the reflected ray. So the ray that's going to be reflected will be at the same angle as the incident ray. We're just going to sketch this rather than measure it. So this angle here should be 30 degrees as well. And then the refracted ray. And what we have to remember is that when we go from the high index of refraction to the low index of refraction, so when we go from an index of refraction of 2.6 back to 1, we're going to see the same angle comparisons as we did up here. And so 63 degrees versus 20, this is a larger angle in the air than in the glass. The same has to be true down here. So let's kind of like really illustrate that. Like we're going to get a big angle of refraction in the air. And so let's really exaggerate that. So this angle here would be our refraction angle. Okay, now we don't know for sure that this is actually going to work. We can draw it, but it may be that we have passed the critical angle. So the last question here is, well, what is that critical angle so theta c, that we can actually have light from the glass transmit into air. And so we can again use Snell's law for this. So I'm going to say N2 sine theta 2, so 2 being the glass, equals N, we'll just call it N3. I think we're talking about a new situation here. Sine theta 3. Okay, so the thing to remember when we're talking about the critical angle is we are looking for this angle, the incident angle. So question mark, when the refraction angle is 90 degrees. So solving for theta 2 when theta 3 is 90 degrees. And so if you remember, or if you don't remember, use your scientific calculator, the sine of 90 degrees is 1. And so I can go ahead and replace sine theta 3 with 1. So sine 90 degrees equals 1. So my Snell's law equation, I'm going to say N2 sine theta c equals N3 times 1. And so sine theta c is equal to N3 times 1. I'll just go ahead and write N3 divided by N2. And so doing the inverse sine of both sides, so sine minus 1 of N1 over N2. Now this equation could be on your formula chart. I don't remember for sure. But it's not a fundamental concept. Like this is something you would need to derive from Snell's law if it was like a derived task kind of thing. So it is something that we need to be able to do. Start with Snell's law, show that we're replacing theta 3 in this case with 90 degrees, or sine theta with 1, and derive the expression for the critical angle. So sine minus 1. So we calculated N2 to be 2.6 moments ago. And then N1, so N for air, would be 1. So theta c would be, let's grab our calculator. So I'm going to do the inverse sign, so shift sign in my case. I'm going to do parentheses, 1 divided by 2.6, and then close the parentheses. And I get something like this, 22.6, we'll call it 23 degrees. So what that means is that when light from the glass exceeds 23 degrees incident angle, we won't have any light refracted through the glass anymore. All of the light will be reflected. So this diagram that we drew up here isn't actually going to work the way that we predicted. We wouldn't have anything transmit through the glass. Everything would be reflected. We would get total internal reflection. Now, we can't get total internal reflection the other way. Like, we can always have light from our air glass boundary transmit into the glass because this angle always has to be bigger than this angle. But down here, because this angle is the smaller angle, we can reach total internal reflection. In this case, we actually do it at a pretty small angle of 23 degrees. And that's because the 2.6 is really, really large. So now you should be armed to attack some of these refraction situations on your own. I will see you guys next time. Till then, ta-ta.